In this lesson, we're going to talk about designing infrastructure protection. The network infrastructure is the foundation of our IT infrastructure, right? And even though it's kind of hidden, it's not customer facing or user facing like applications or services on the network. If the infrastructure and the network foundation isn't secure, then the applications that ride on top of those, that infrastructure are not going to be secure as well. So we definitely have to take security into consideration when we're designing our network infrastructure and our network foundation. And that's part of that defense in depth approach that we talked about. All right. So what we're going to talk about in this lesson is the Cisco network infrastructure protection components. We're going to talk about how to protect access to devices in the network. How do we protect our routing infrastructure? How do we protect our network devices? How we enforce policies on the network infrastructure using layer 2 and layer 3 data plane security controls, and how we secure our switching infrastructure. So this gets into really a lot of the CCNP route and switch concepts when we're talking about protocols and devices and elements on the network that we need to protect. The first layer in securing your network infrastructure is the enforcement of really fundamental, critical, whatever you call it, network security elements. And this forms something called our baseline security. The fundamental elements of network security, which create this strong foundation, typically have always been very basic concepts, right? Making sure that we have physical access control to our devices, making sure we have the appropriate authentication mechanisms to the devices so we can authenticate to the devices appropriately and so on. But we have graduated from that basic network foundation security to a much more advanced method and much more advanced techniques to secure our control plane functions, our routing functions, our communication functions. If, as a network security practitioner, you don't address the elements of this baseline security, then the rest of the security elements that you put into place are essentially useless. All right? So we need to make sure that we secure our infrastructure device access. We need to make sure that we secure our routing infrastructure. We have to make sure that we have availability. That's part of that CIA triad: confidentiality, integrity, and availability. So we have to design in resiliency and survivability. We need to make sure that we have the ability to capture network telemetry and be able to identify the policy enforcement points on the network and secure our switching infrastructure and so on. Lots and lots of different aspects. The functionality of a network device, and we saw this in one of our previous lessons, is broken up essentially into 3 planes of operation: the data plane, the control plane, and the management plane. To provide a complete kind of a turnkey security solution to the network device, security has to be enforced at all 3 planes of operation. We have to protect the management plane by specifying or focusing our security infrastructure's device access requirements. The control plane protocols need to be secured, being our routing protocols and whatnot. And we need to secure our routing and switching infrastructure to protect the control plane of our network devices. The data plane needs to have some sort of security enforcement for network access policies and secure switching and so on. And that's what this whole chapter is really all about. That's what this whole lesson is all about, is looking at that network foundation security. Securing the network infrastructure means that we have to secure management access. And this is one of those three control planes of existence or planes of operations that we talked about. You know, it's very simple. We want to prevent unauthorized access to the network, okay? Securing management access to the infrastructure devices, well, let me put it a different way. If the access to our devices uses a substandard set of security principles, it doesn't matter what other security elements we implement in the other planes of operation. We can have lots and lots of security on our routing protocols. We can have lots and lots of security on our telemetry protocols like NTP and our syslog operations and our SNMP operations using SNMP with encryption and authentication and everything else. But if somebody can access the devices because our management access isn't secure, then it kind of negates the whole point of all those other security features. All right? So we need to prevent unauthorized access to our devices. Network infrastructure devices obviously give us a lot of different ways to access those devices. And many of them are actually enabled by default and not necessarily in the most secure fashion. All right, like Telnet, for example, being the default transport for our in-band management. So we need to review and properly configure every device that's implemented in our production environment. There are some key points of focus, right? We see them listed on the slide here. The key points of focus when securing management access include things like restricting device accessibility, all right? Limit the permitted methods of access to only those that need management. Limit the scope of IP addresses that can access the device. Limit the protocols that you can use to access a device. For example, don't use Telnet, use SSH, and so on. Use access control lists to identify who can access the management plane and from what IP address or what subnet that they can access the plane from. Make sure, and this is not a technical control, this is more of an administrative control, even though it's implemented technically, present legal notification, right? Make sure you have a notification banner on all your interactive sessions so that the person that's connecting to the system gets notified if a security policy is being enforced. Kind of, you want to do that anyway, right? Even if there isn't a security policy being enforced, you want to make it appear as that there's a security policy being enforced. Oftentimes, that will simply deter anybody from accessing that system, even though those enforcement points might not actually be active. Of course, from a fundamental standpoint, we want to authenticate access, right? Authenticate the users. Make sure that the devices accessing the network are granted to specific users, groups, and even once they're accessing the device, what kind of services can they run, what kind of functions can they perform on the network, right? As opposed to just giving them carte blanche access simply based on an authentication profile. So authorization is a big piece of that, right? Not only do we authenticate the users, but we need to authorize the users, the actions they can perform, the views that they're permitted to see, and we call that's part of our AAA architecture, right? Authentication, authorization, and then accounting, right? We need to make sure that we're using confidential protocols, right? Whether it's stored sensitive data, that allows us to copy and move stuff back and forth, or whether it's data in transit, using protocols like Telnet or HTTP, which sends everything in plain text. Nope, we don't want to do that. We want to use SSH, HTTPS, and so on. And then we want to account for everything. We want to make sure that we have logs, record who's accessing what devices, what the person was doing when they were accessing the device, and so on. These are CCNA security principles, right? Very, very basic principles, but they're definitely very important concepts that we need to address. We have lots of tools and mechanisms that exist today to protect the network infrastructure devices. And we need to deploy those tools, but it's very, very important. We need to make sure that we're deploying those tools in an effective manner. Oftentimes, and we see this with customers quite a bit, they implement tools and mechanisms to secure the network, but by default, those tools and mechanisms aren't implemented as a best practice or in a best practice function. So you get this false sense of security that says, hey, I'm running SSH. Great. Yeah, you're running SSH, but you're running SSH version 1 point something. You're not using AES, and you're also using RSA 768 or whatever. So it's not enough just to say, let's implement these tools. We also need to make sure that we're implementing the tools in the best way. All right? Now, there are generally two independent mechanisms to secure management access to our infrastructure devices. We can use out-of-band management, right, establishing some sort of logical or physical separated network for management purposes, and then that network allows us to isolate from the network that's forwarding user traffic, so there's no chance of spoofing or interception of management traffic. I wouldn't say no chance, but it's definitely a lower chance, right? In that case, it might be, although I wouldn't say so, it might be acceptable to use a clear text protocol or some sort of plain text management protocol, even with weaker authentication, all right? Again, I'm not going to recommend that because oftentimes using the enhanced protocols doesn't require much more effort than using a plain text protocol, right? Using Telnet, quite frankly, is just as easy as using SSH and vice versa. The other option is to do an in-band management and have some sort of in-band management philosophy where you're using protocols like SSH, HTTPS, SNMP version 3, and so on. But because the traffic, the management traffic is passing over the same network that user traffic is passing over, we want to make sure that we have cryptographic protection like IPsec, like VPN, and so on, to address that, that fact. It is also recommended that we deploy IP address-based filtering to allow access to the device management plane only from trusted network sources, trusted network devices. For devices using Cisco iOS software, there's lots and lots of different ways we can limit access to the management plane. We can use access lists, which deny access to everybody but specific management IP addresses. We can do service-specific ACLs to limit specific protocols or to limit access to a particular VTY line. We can use iOS software control plane protection and control plane policing. COP and CPPR, which allows additional access control protections against that virtual control plane interface that exists at the control plane level. We can also use management plane protection. That lets us designate an interface of the device as the only interface in which management traffic is allowed to and from that device. We see this in a lot of modern network devices today where they have separate management interfaces for that particular process, okay? When it comes to network communication, of course, one of the biggest pieces and one of the most important pieces for a multi-layer and a multi-domain network is routing. And if routing isn't working, the network isn't working. So protecting our routing protocols is really, really important as well. A routing protocol needs to be protected so that we don't see unknown peers or spoofed routers or rogue routers being injected into the network, causing these fake routing updates through the routing protocol. Meaning that we only want to trust routers based on security principles as part of our routing domain. Okay? Most routing protocols today support both clear text password authentication, where the password is actually included in the routing update, and a hash-based algorithm to produce messages and authentication in the updates. If I'm using message authentication code, the way that it works is it's a very simple process. I've got a router here that wants to send a hello packet or whatever to another router. I take that data, that hello packet or whatever it is I'm trying to authenticate. I have a hashing algorithm, in this case MD5, that I want to put that hello packet through, but I also have a key. All right. Now the key is never shared across the channel. The key is simply used. It's a pre-shared secret key, but it's the secret sauce that goes into the hashing process that ensures that we're protected from man-in-the-middle attacks, because the man-in-the-middle doesn't know the key. And then out pops something called a MAC, the message authentication code. That MAC gets sent along with the hello message or the routing update or whatever it is in plain text, and the router that receives that information on the other side goes through the exact same process, takes the hello, takes the secret key, puts it through the hashing process, and if the MAC that was sent matches the MAC that was calculated on the receiving side, we've done two things. We verified the integrity of the data, it hasn't been modified in transit, and we've also verified the authenticity of the source, because the source is the only one that knows the secret sauce, the key that goes into the process. This is how just about any digital signing, or it's a little bit different with digital signatures because we don't use a pre-shared key, we use a RSA key pair, but same general concept, right? So a shared secret key is combined with the information that's in the packet. We calculate a hash from that combination, and then only the sender and the receiver that are legitimate would be able to identify that hash result and verify the hash result. Different routing protocols have different authentication methods, and this, by the way, applies to IPv4 only. Remember, in IPv6, IPsec is built into IPv6, the IPv6 protocol suite. So we don't use these methods for authentication in IPv6. We use the native IPsec and AH, or ESP and AH components that are part of the IPv6 protocol suite. So RIP, clear text and MD5, OSPF, clear text and MD5, EIGRP, MD5 only, and BGP, MD5 only. When we're implementing routing protocol authentication, a couple of things to point out. Authentication occurs when a broadcast segment is shared by routers and untrusted end stations. I mean, this is where we would typically deploy it, so that somebody in the network, they can still see the routing protocol updates, they can see the queries, they can see the replies, they can see all of the different routing protocol messages. And by the way, every single routing protocol message type has the hash applied. In EIGRP, we have hello packets, we have updates, we have queries, we have replies, we have acknowledgments. In OSPF, we have link state advertisements, we have link state updates, we have link state requests, link state acknowledgments, DVD packets, and hello packets. So in either case, every single packet that gets generated has this MAC associated with it. Whenever possible, of course, you want to use MAC, HMAC, MD5 over plain text authentication. Okay? And by the way, you will see hashing protocols just written as MD5 or just written as SHA, right? And this information on the slide is a little bit outdated, because some of my more modern protocols also now support the secure hashing algorithm. not just MD5. OSPF supports SHA now as well. So we have MD5 and SHA, but when you see HMAC tied to that, that is that secret sauce. That means that we have the shared secret key process as part of the hashing process. All right? Make sure you deploy really strong secret keys because typically speaking, these keys are not changed on a regular basis. The keys themselves are pretty static. So to increase the work factor, if somebody's trying to perform cryptanalysis on these sessions and trying to discover the key so that they can intercept the data and modify it or whatever, you have to have really strong cryptographic keys, what we call the crypto variable. I mean, hashes are pretty much irreversible. The only way to really effectively break a hash is to use a brute force method, maybe rainbow tables or some other brute force method to try and discover the crypto variable that goes into the hashing function. If we're changing the keys, make sure that we use a rollover function, right? Don't just stop using one key and start using another key. There has to be some overlap because the key lifetimes are dependent upon the times that are on the local device. And maybe those times are not always synchronized. Even if they're closely synchronized, they may not be exactly synchronized. So you might end up breaking your routing domain by shifting over your keys. All right? When we're securing our routing protocols, it's also recommended that we use passive interface. Passive interface suppresses updates and hellos and whatnot from going out of an interface, even though that interface might be part of the routing domain. And it's kind of like establishing a need-to-know basis for routing information. If there aren't any routers on an interface, we still want to include that interface in our routing process because we want to be able to advertise that network, etc. But we don't necessarily need to share that routing information with the folks on the local LAN because they're not part of the routing domain. And there's no other router on that segment that needs to hear routing information. So what do? We use passive interface. It still allows the protocol to include that network in its routing updates and advertise the route, but it essentially suppresses that routing information on any interface that's passive. It's a basic concept. We learn about it in the CCNA routing and switching class. All right. All right. The other aspect that I wanted to talk about before I move on from this slide here, BGP also supports some additional checks. This is not something that's available in OSPF or EIGRP, but it checks the TTL value. In BGP, this feature is called a TTL security check. And it was actually, if you guys are familiar with BGP, this is not something crazy that you may not have heard of. It may not have heard of it called a TTL security check, but you know that this is a restriction that eBGP peers have, right? And it's actually by design to protect against forged IP packets for external BGP peering relationships, all right? There is a minimum TTL value for incoming packets when we configure BGP. BGP will establish and maintain sessions only if that TTL value in the IP packet header is greater than or equal to the TTL value that's actually configured in the BGP session. And by the way, that's 1 by default, right? If the value is less, then the packet is discarded. There's no ICMP TTL exceeded message that gets sent back. We just simply don't accept that BGP packet. This, by the way, is where we would have to use the BGP the BGP multi-hop command, right, to change the TTL value. We can control routing information that's accepted or transmitted to and from known peers as well by using route filtering, right? We can use prefix lists and distribute lists and whatnot to identify what routes are actually shared. By default, most routers, in fact, just about all routers, if they become peers, they share everything automatically. Well, for extranet connections and for connections that leave the domain that we have control over, this might not be something that we want to happen, okay? So we can use route filtering to accept or transmit only specific information or good information or whatnot. I mean, there are lots and lots of tools that we can use, distribute lists, prefix lists, community lists, redistribution with route filtering. We can do summarization. We can do null-zero route summarization. I mean, there's a bunch of tools, and we learn about all those tools in the CCNP class to facilitate and protect the amount of information that's being shared back and forth, right? The next thing that we'll talk about is device resiliency and device survivability, okay? Routers and switches are subject to attacks that affect their functionality just like any other device. In fact, in Kali Linux, one of the classes that I teach is a GSEC class, GIC GSEC class, and CEH as well. CEH doesn't focus on this nearly as much, but it's more application-based. But the GSEC class is kind of a general, more of a general CEH type class. And we use a tool inside of Kali Linux called Yersinia, Y-E-R-S-I-N-I-A. And Yersinia allows us to, it's a tool specific for launching network-based attacks. Attacks against CDP, attacks against LLDP, VLAN hopping attacks, spanning tree attacks, and they can be denial of service, they can be spoofing, et cetera, et cetera. There are a lot of protocols that run on our routers and switches that are automatic. VTP, spanning tree, DTP, 802.1q, and routing protocols and whatnot. The whole point of these protocols, spanning tree, of course, one of the most important ones. The whole point of these protocols is to make our network resilient and to allow the network to automatically recover from faults and failures and issues. But those are automatic features. And as I stated the other day, automatic means it's generally susceptible to some sort of vulnerability. Whether they're denial of service attacks, distributed denial of service attacks, flooding attacks, reconnaissance attacks, and so on. I mean, just the two protocols that we use the most often in networks, ARP and DHCP. ARP spoofing attacks, ARP poisoning attacks, ARP flooding attacks, ARP discovery attacks. I can list hundreds, well, not hundreds, but a lot of different types of attacks just on the address resolution protocol. Same with DHCP, starvation attacks, which is a denial of service attack. And then we have our man-in-the-middle attacks, so DHCP spoofing, and so on. So we can do phishing attacks and farming attacks and insert ourselves into the conversation. All of this is related to network infrastructure devices. And the protection mechanisms that we have to use have to come directly from these network infrastructure devices. To follow best practices, there are a few things that you should do, right? Number one, Cisco devices, and I'm sure other vendors are the same way, they come with a lot of services enabled on them by default, particularly routers. Switches, and not so much, right? Switches generally are just a switch, but you know, you can get some of the enhanced switches today that have a lot of these features enabled as well. And these switches, out of the box are turned on, but you may not, I mean, not switches, services, sorry. These are turned on and you may not need them. Things like boot P, IP source routing, PAD services, IP-directed broadcasts, proxy ARP. You need to disable these services. There is a tool. It used to be on Cisco's website. I hope it's still there. I haven't used it in a very long time. It is called the Output Interpreter tool. So if you go to Cisco.com and you log in with your CCO account and you search on Output Interpreter, okay, you will find a tool that you can use. You can paste your configuration into this tool, and it will identify all of the network foundation vulnerabilities that that particular device is susceptible to. It'll tell you if services are enabled. It'll tell you even how to disable them. It'll even tell you what those services are for, you know, because sometimes you may want those services running. So it's a great little tool. I used to use it a lot when we were doing network assessments and vulnerability assessments on the network. It was a great tool to use. Provided a lot of input. We need infrastructure ACLs. This is another network foundation protection mechanism. An infrastructure ACL is a traffic filter on the network edge, typically applied in the input direction on the interface that connects to the network where the users are attached, or even in the other direction where the external network is attached. And it's configured so that it drops and logs traffic that's destined to IP addresses of the network infrastructure devices, and it permits all other traffic. What's the point of an infrastructure ACL? It's to block spoofed addresses, right? So for example, I should never see 127 addresses on my network. I should never see traffic coming from RFC 1918 addresses on the outside interface of my firewall or my router. Conversely, I should only see RFC 1918 addresses and specific RFC 1918 addresses leaving my network. So we can create these infrastructure ACLs that essentially blocks those subnets, because those are that will block a lot of different types of spoofing attacks and so on. Make sure you implement redundancy. Networks are built from lots and lots of hardware and software components. Those hardware and software components can fail, whether it's because of a hardware failure, because some idiot unplugged a cable that they weren't supposed to unplug, or whatever, or even just because of some sort of denial of service attack. So if we have redundant components in the network, we prevent those single points of failure. We improve the availability of our network and make it much more resilient to attacks, okay? The last bullet point that's on this slide here is to protect the devices using control plane protection and control plane policing. COPP is our control plane policing, and CPPR is our control plane protection. What COP does, COPP, is it rate limits and drops traffic destined for the central processor of our network device. This is based on policies that are applied to a virtual aggregate CPU-bound queue. That is called the control plane interface. Very, very important function here. By the way, this is not enabled by default in any fashion. So there is no default protection against control plane attacks, okay? The queue, this control plane interface, or the CPU-bound queue, it receives all of the aggregated traffic that's destined for the control plane, actually the master plane and the data plane as well, that has to be software switched, right? So there is certain types of traffic, if we're using things like Cisco Express Forwarding and even a certain level of fast switching techniques, that doesn't necessarily have to go through the control plane, okay? But there are lots of types of traffic that actually have to go through the control plane. Traffic that doesn't match a CEF profile. If we're using fast switching initial packets that allow us to build the caches and whatnot, that has to go through the control plane, okay? Similarly, the CPPR, Control Plane Protection feature. It also rate limits and drops traffic destined for the CPU. All right? The difference between COP and CPPR, though, is that COP isn't predefined. You have to set up classes of traffic. You have to define the classes of traffic. You use MQC to do that, class maps and policy maps and so on, to apply your control plane policing functions. CPPR does rate limiting as well, but the traffic automatically gets classified into 3 different queues. There's a a control plane host interface. All right, so the control plane host interface is traffic that's directly destined for one of the router interfaces. So it might be an SNMP message or an SSH message or an IBGP message and so on. And that's the host control plane host subinterface. And then we have the Cisco Express Forwarding Exception subinterface, the control plane Ceph subinterface. Now remember, data that matches a Cisco Express Forwarding profile doesn't ever touch the control plane. It gets processed through the ingress and egress interfaces on the data plane because of the various caches that we've built, a forwarding information base, a MAC address table, et cetera, that allows that traffic to be passed through. So traffic that matches a Ceph profile doesn't ever hit that control plane. The control plane Ceph exception subinterface is traffic that gets redirected either because you configured an input feature in the Ceph packet forwarding path to make sure that we process switch that packet, or it's directly enqueued in the control plane input queue by some interface driver and so on. And basically, it's traffic that's not going to match our Ceph profiles. ARP, eBGP, LDP, label discovery protocol, etc. Those are the types of things that might actually have to be process switched and can't be Ceph switched, right? And then we have the control plane transit subinterface. This is the third of the 3. The first one was the control plane host subinterface. The second is the control plane Cisco Express Forwarding exception subinterface. And then the last one is our transit subinterface. This is all traffic that is software switched by the CPU. All right, so these aren't exceptions to Ceph. These are just traffic that can never use Ceph, right? And not use Ceph for a forwarding purpose or forwarding process. I don't know if we're going to see details of COPP and CPPR, but if you're interested in actually looking at these specific components, if you just go to Cisco.com and search on Network Foundation Protection, NFP, you will see documents, lots and lots of documents on establishing policies, control plane policing and control plane protection policies, because these 2 things are really the cornerstone to protection of the control plane in our device. All right? It's actually something that a lot of people don't implement, but they should. It's almost equivalent to saying, I'm going to use Telnet instead of SSH. Why the heck would you not use SSH, right? And use a plain text transport for your management. All right. Baseline network policy enforcement, that is the primary concern. Well, it is a primary concern, but the point is that we're trying to ensure that traffic entering a network conforms to a network policy, including the IP address range, the different traffic types, etc. Anomalous packets should always be discarded, but where should they be discarded? Right? They need to be discarded as close to the edge of the network as possible. This is going to minimize the risk of our exposure, and it's going to ensure that we're not wasting bandwidth, wasting resources, processing data that should be dropped eventually anyway. All right. Now, in order to do this, there are two things that you need to implement as part of your baseline network policy enforcement. One is access edge filtering, and the other is IP address spoofing protection. Okay? All unnecessary traffic needs to be filtered. And you should do it, right, as close to the edge of the network as possible. Protect access to the devices themselves using these infrastructure ACLs. We already talked about what an infrastructure ACL is. We can control what traffic is allowed to the device and what traffic is not. But we should also filter traffic to the internal networks at the edge of the network. And that's just basic common knowledge, right? And we call those transit ACLs. Basically, it's just another form of an access list. They don't, from a syntax standpoint, they're no different than infrastructure ACLs. It's just a matter of what they classify, right? But essentially, a transit ACL is any access list that's used to filter traffic that's going through the box, through the router, all right? We should also only permit and authorize traffic to the internal networks. Spoofing protection is a very important concept. When we're enabling or utilizing a protection mechanism for spoofing, we're trying to discard traffic that has invalid IP addresses. Now, we can't always guarantee that the traffic is valid or invalid, right? But there are definitely certain things that we can look for and certain things that make sense that should be considered invalid. For example, like I said before, the RFC 1918 address range, which is our private address range. We shouldn't see traffic coming from that range of networks from the internet side of the public zone, right? We should only see those types of addresses in our enterprise, okay? In addition, even within that RFC 1918 address space, there are specific types of IP addresses that should never be seen. 127 addresses should never be seen. 240 to 254 addresses should never be seen because that's the experimental range. 239 addresses up to 224 to 239 addresses should never be seen as a source address because that's our reserved multicast range. So we know that these are very easy, an easy set of address ranges that we can identify very clearly in our enterprise as potentially spoofed addresses. To limit the range of possible IP addresses for IP spoofing attacks, you also kind of want to know what your valid network ranges are, right? Implement filtering. There's a specific RFC. They don't have it listed on the slide, but I always tell my students about this RFC. There is an RFC 2827. Okay? That RFC was specifically written to identify what types of network address ranges you should filter based on. So I would definitely take a look at that. All right? Now that should include addresses from RFC 1918, special use IP addresses, non-allocated IP address ranges, and so on. Obviously, not everything's going to apply internally, but certainly externally. All right? Only allow traffic that's originated from your network block out. So not only are you trying to protect yourself from spoofing attacks from the outside, you need to protect the outside from spoofing attacks from the inside. All right? So it's definitely, and that's something that's pretty simple to do, right? Because we know what types of networks we have on the inside of we know what address blocks we're using, and we know what address ranges we're using. All right? What are some of the methods that we can use to filter traffic coming into our network? Access control lists. Simple, right? We can use something called Unicast Reverse Path Forwarding, or URPF. This is covered on the exam, so I'm going to mention this real quick. It is a technique. It's a dynamic technique, and the goal of URPF is to identify that the traffic is coming from a known source. Not only is it coming from a known source, it's coming in the router in the right direction, right? So what happens is this application will discard packets that have invalid source IP addresses based on the router performing a reverse path lookup in the routing table, okay? Let me explain. If I have a packet that arrives on a router on gigabit Ethernet 00, and that packet is sourced from x.x.x.x, I am going to look into my routing table, and I'm going to see if I have a route to network x.x.x.x, and if that route matches the interface that the packet came in on. There's two ways to do this. You can do this in a loose way, or you can do it in a strict way. So, and that usually just means whether or not we're matching on an exact routing table entry, or if we're also allowing the default route to be used. But essentially, the router's basically saying, okay, I just got a packet on this interface from this source. Do I know how to route back to this source, number one? And did the packet come from where it was supposed to come from based on my routing table? Okay? If the packet doesn't match, then we drop it. If the packet matches, then we forward it. It's not based on the destination. It's always based on the source, because we're doing reverse path verification, not forward path verification. All right? All right? I was going to say something, and I can't remember what I was going to say. The acronym URFP, it's a little confusing, right? Because it actually stands for Unicast Reverse Packet Forwarding. But for some reason, the acronym is listed as URFP. So it's a little confusing. But anyway, that's what it does. We can do source guard, right? Source guard is used in switched environments, very much like, kind of like URFP. It denies the use of forged or fake MAC addresses and IP addresses. So we deploy this in our switching devices, and it's designed for typically segments that are running DHCP. Static addresses are supported, but it requires some static configuration and so on, so it's not easily deployed. But a source guard kind of allows us to identify MAC address and IP address bindings, and it's based on DHCP snooping, which builds an IP to MAC address binding database that maps information to ports and MAC addresses and IP addresses, and we can verify the validity of IP packets based on that binding database. DHCP snooping, ARP inspection, these are also protection mechanisms, right? ARP inspection is used to protect the ARP process, the query process, the reply process, to prevent ARP spoofing, MAC address spoofing, and to prevent ARP poisoning attacks. And it also works with the DHCP snooping binding database. So it's kind of a little bit too much to go through all of these tools specifically in this class, because we learn about those tools in the CCNP route and switch class, but these are things that you should consider implementing, right? Finally, switching, right? Baseline switching security, that's going to be concerned with ensuring the availability of my layer 2 network. And there are some best practices that we need to follow in this realm as well. One of the key things that we need to be concerned with, and it's probably the most important aspect of a switching environment, is spanning tree. And Cisco has done a really, really good job at introducing what we call the spanning tree toolkit. It includes BPDU guard, BPDU filter, loop guard, root guard, ether channel guard. There's just a whole bunch of different tools built into spanning tree that provide these protection mechanisms for our spanning tree domain. And not all of them should be used, right? BPDU filter, I never really quite understood why that would be necessary, but it's generally not recommended. But certainly BPDU guard, root guard, disabling VLAN trunking protocol like DTP. There's a whole bunch of stuff that you have to be concerned with, all right? Now, we know that in switching, we try to limit the size of our broadcast domains by creating VLANs. We need to concern ourselves with spanning tree security because, again, it's a dynamic protocol. It sends and receives BPDUs, and based on those BPDUs, we change our topology. So it's very susceptible to attack, all right? So we have to have those protection mechanisms in place. Traffic filtering mechanisms. A lot of people are not aware, but just like I can create access lists at layer 3, I can create access lists at layer 2. In the CCNP T-shoot class and the CCNP switch class, you learn about VLAN filters. You learn about PACLs, port-based ACLs, and VACLs, VLAN-based ACLs. And then we also talk about things like port security, enabling MAC filtering on a port based on a specific MAC address or a number of MAC addresses or whatever. We can do static or dynamic or sticky configurations in that case. There are some VLAN best practices. Cisco's doing a better job at this now with their modern iOS, but in the past, we had protocols automatically running on our switches like VTP, the VLAN trunking protocol, like DTP, the dynamic trunking protocol, that opened up a huge vulnerability in our layer 2 network, okay? To the point where I could go into a network without ever logging into a switch, without ever even accessing any of your devices, get a copy of your VLAN database, overwrite your VLAN database, disable all the ports without ever even touching your command line, right? All I would have to have is my own rogue switch to do that. So there are some VLAN best practices, right? Make sure that you implement, disable DTP by doing switch port no negotiate or switch port mode access. Make sure you disable VTP by running your switches in transparent mode. You can even extend your VLAN best practices to include things like running private VLANs or protected mode, switch port protected mode on your ports. There's a whole bunch of different things, and we talk about using a native VLAN, for example, as our black hole VLAN. Assigning unused ports to a black hole VLAN. Lots and lots of different things. All right. We need to make sure that we don't forget about layer 2. Layer 2 is very important. There are lots of filtering mechanisms at layer 2 that you can use. Storm control, I didn't even mention that. Port security to protect against MAC flooding attacks and CAM overflow attacks. Storm control if we get a broadcast storm, just by malicious attack or by mistakes a network configuration. All right. VLAN filtering on our trunks, restricting different VLAN IDs on the trunk to only allow the VLANs that are needed across that trunk link. Disabling unused ports, putting them into an unused VLAN. Not using VLAN 1 for anything. You can't do that 100%, but you can certainly not use VLAN 1 for user traffic. Configure all the user-facing ports as non-trunking ports, making sure that we're disabling the dynamic trunking protocol. You guys probably already do this. It's just a simple command, switch port mode access, right? Explicitly configure trunking on your infrastructure ports. In other words, make them trunks. Don't allow the trunks to be negotiated. Use tagging for all of your VLANs, including the native VLAN. Set the default port status to disable. if you don't want those ports to be used by default. Okay, because all switch ports are turned on by default. So I don't think I told you guys anything extraordinary. You know, I mean, I'm sure that we didn't bring out any revelations in this case. You guys are all CCNPs, so you've heard this stuff before, right? Which makes it a little bit easier to understand, of course. So in this chapter, we talked about the enforcement of fundamental elements of the network to create that strong network foundation and security at the network foundation. Securing access to the infrastructure devices, preventing unauthorized access, protecting routing infrastructure with authentication and applying different types of route filtering techniques, preserving the resiliency and the survivability of the network devices by using best practice standards. And that transcends the layers, right? I mean, in the foundation, we're really only concerned about two layers, layer 2 and layer 3, but this is a principle that needs to be applied to both of those layers, right? Enforce your network policy with the idea that you're going to extend that policy to the edge of the network to protect against things like IP spoofing and MAC address spoofing and so on. And then don't forget the switching infrastructure. Everybody always thinks about routing. They think about access lists. They think about filtering packets because packets are end-to-end, right? So we typically will think about filtering packets in that regard. But it's important to understand that the switching environment is just as critical, and we have to protect that environment as well. So that is the end of that lesson. The next lesson we're going to get into is firewalls and IPSs and IDSs, and then we'll look at network access control.